Hi guys, we're going to go over some things about forces in an elevator today. And you're going to do a simulation on it. Watching this lesson and completing the elevator ride packet will be part of today's and Tuesday's assignment. You'll have both days to watch all this and complete it. And your next assignment will be on Wednesday. Okay, so we've been doing a lot of stuff in the past couple of weeks with forces. We're going to focus right now on vertical forces in such a way, the scenario we could all relate to, because I'm sure we've all rode in an elevator many times in our life, right? And we're going to go over 4 general scenarios that happen in the elevator, but we're going to do something a little bit weird. We're going to imagine in an elevator that we are standing on a bathroom scale. All right? And the reason why we are going to pretend this, there's our bathroom scale, right? Here's the elevator floor, bathroom scale. Here's you. The simplest scenario we're going to take first is that we're at rest in an elevator on a bathroom scale. And if the elevator is at rest, and by the way, that means acceleration equals 0. Okay? If we're at rest, we might as well be just in a bathroom on a bathroom scale, right? So that's the first simple scenario. And what does a bathroom scale do? It reads your weight. But we got to realize why it reads your weight. All right? And because in the wrong scenario, a bathroom scale will not read your weight. It only reads your weight when we're in something called equilibrium. All right? And we're going to discuss that in a second. It's spelled like this, equilibrium. Back when we first started, it seems like a while ago now, back when we first started this unit on forces, there's a lot to it. We went and had a vocabulary assignment and a vocabulary quiz, and one of those words was equilibrium. All right? And to be in equilibrium meant you had balanced forces because you were not accelerating. And there's really 2 ways to not accelerate. One of the 2 ways is at rest. The other one is to be moving at constant speed. Okay? So I'm going to draw a free body diagram right on top of our person here that represents us. Okay? So if you're just standing on a bathroom scale in an elevator, your weight, or in other words, the force due to gravity, let me draw it down a little bit more, points downward, right? And the normal force points upward. The normal force in a different color maybe here. That one doesn't show up too well. I'll just use red for all of them. And the normal force points this way. Now we've all been on a bathroom scale before, and we know for it to work we have to stand very still. Alright? So if we're standing very still in an elevator and the elevator is not moving at all, not accelerating in particular, but in this case not moving at rest, then these 2 forces balance. And that's proven through Newton's second law, which we have dealt with recently. Last week we had some assignments on this. Newton's second law says the net or total force on an object is equal to ma. So the only forces we have here are on the y-axis, and that's what we're going to focus on. The total forces just making up positive and down negative. So that would be the normal force minus the weight. When I total up the forces for F net, we've done this before. Since there are only 2 forces, but we don't put an addition sign there because they're not pointing in the same direction. The one pointing up minus the one pointing down equals ma through Newton's second law, but a, since we're at rest, acceleration 0. And it doesn't really matter what this person's mass is. 0 times anything, this whole side's 0. And what it shows me is that the normal force equals my weight when we're on a bathroom scale at rest. All right? And what that really means is that in that setting, the normal force is the scale pushing back on you. So we might as well call this normal force the scale rating in this scenario. That's what the scale will read. But since it's a surface pushing back on you, technically, that's what we defined in the past as a normal force. And don't forget, F sub g is also known as your weight. Force due to gravity is your weight, right? So this proves, through Newton's second law, that basically you need to be in equilibrium on a scale for it to read your real weight. So for example, if this person was 800 newtons, remember, newtons are a unit for all forces. If our person was 800 newtons in real weight and they stepped on a scale, that scale should read 800 newtons. They're balanced. They're equal to each other. All right? Pretty simple, right? So when these forces are equilibrium, well, in an elevator, let's get a little more exciting now. An elevator that is moving, but moving at constant velocity. So let's draw our vacuum scale again in our elevator, and us again. We're going to be moving with, I'm going to abbreviate there, constant v. I don't care if it's up or down. I'm just going to write up or down at constant v. A is still 0. Constant velocity means we're not speeding up or slowing down, right? So actually, we would have the same scenario as the last one. As long as it's a smooth riding elevator and it's not jerky, your weight, well, it still points down no matter what, and normal force still points up. And for the same reason, since A is 0, if we set up Newton's second law again, I'm going to go right into it, F net again is the normal force minus the weight, and that again equals m times 0, which is all 0 on this side. And this again proves to me that the normal force equals the weight of the object. So again, if this person's 800 newtons, okay, I'm just using that as a makeup number. If this person's weight is 800, the normal force or scale reading is also 800 newtons. Why? Because there's no acceleration. So basically, what this is telling us, for a scale to read our weight correctly, like a bathroom scale, it has to be in equilibrium, either at rest or constant velocity. All right? The needle on the scale, or if it's a digital scale, the reading on the scale, the number on the scale will equal our weight. But if you went in, let's not even have an elevator here. If you went into your bathroom on your scale and just started bouncing up and down on it, that needle or digital number will just start going everywhere. It'll be chaotic. Why? Because you're not at rest or constant velocity, are you? If you're bouncing up and down, you would have a non-zero acceleration. And that would change the result of the scale reading. It will make you feel heavier at times or lighter at times when you have a non-zero acceleration. But when you're in equilibrium, that is either at rest or constant velocity, back to the elevator now. So if you're in this person in this elevator and you're an 800 Newton person and it's at rest and you're standing still and look down, the scale should read 800 Newtons. If you're moving up or down at a smooth, constant velocity in an elevator, it should read 800 newtons. But what happens when the acceleration is not 0? That's the next question. Okay? So again, scenario 3. There's 4 general scenarios. This is number 3. Floor of the elevator, bathroom scale, U again. But this time we're going to be undergoing a positive acceleration. And by the way, now that I'm noting that, abbreviate it. Some positive value, positive acceleration. We'll put a real value in a second, but let's just keep it general for now. We have a positive acceleration, and stuff we learned in the past, we don't have to be going upward to have a positive acceleration. There's 2 ways to have a positive acceleration in an elevator. You could be moving downward and slowing down. That would give you a positive acceleration. Or you could be moving upward and speeding up. That would also be a positive acceleration. Just the main point is, don't assume just because you have a positive acceleration you have to be moving up. Okay? You could actually be moving down and slowing down. That would still be an upward net force having an upward acceleration on you. Positive being the upward direction. Alright, but what happens in this case? If you would look down on the scale while you're in this elevator and you have a positive acceleration, you will not feel like your real weight. Remember, using the example number before, the number I've been using, let me make a smaller vector arrow here, so it makes sense. The number we've been using has been 800 newtons, right? So if just a real person's weight is 800 newtons, and I'm experiencing a positive acceleration, we actually feel heavier, and the normal force, aka the scale reading, of the scale pushing back on you, no longer is 800 newtons. What is it? Well, it's going to be heavier. And we'll prove that right now, because we're going to set up Newton's second law like we've been doing. Normal force minus weight is the net force, equals ma. But it's some positive acceleration. So let's, to complete this example, now put in a specific acceleration. Let's say the acceleration is a equals positive 2 meters per second squared. Okay? So if I wanted to know the scale reading, remember this is not 0 anymore. I would also need to know the mass of the person. And we learned something before, that mass is found by taking the person's weight, which is 800 newtons, and dividing it by 9.8. Changing weight to mass, we learned a little bit about that in the past, so I'm going to do that. Don't worry too much about the math. I'm using the math myself to prove this to you guys, okay? Just so you don't take my word for it. The concepts are what matters the most to you guys to do the simulation you're going to do, but still try to follow along with me. So this guy that has a weight of 800 newtons would have a mass of 81.6 kilograms. Just a quick review. The difference between mass and weight is mass is how much stuff you're made up of, how much matter. So this guy's made up of 81.6 kilograms of matter. And weight, or force due to gravity, is how much gravity is pulling on your mass on whatever planet you're on, 800 newtons. So this is the person's mass, and this is the person's real weight. Why do we know this is real weight? Because we already said in the last scenarios that was what the scale would read if we were in equilibrium at rest or constant v. And now we have a positive acceleration. So the scale reading is the normal force. And to solve for it, doing some basic algebra, we would add the force due to gravity, aka weight, to the other side. And I would plug in the numbers. I found out why mass was 81.6. The acceleration's positive 2. And I would add that to my 800 newtons. That's what Newton's second law, the math, is telling me to do, right? And that would figure out that this person in this condition, if I run these numbers correctly, I hit one wrong button there, let me do it again, 800 plus, I hit it times, 81.6 times 2. This person would feel like they were 963.2 newtons. In other words, generally speaking, when you're accelerating positively, any positive value in general, the normal force, aka scale reading, I'll just remind us of that by putting that in parentheses there, is greater than your actual weight, force due to gravity. So the big concept that you really want to remember here is that when you're undergoing a positive vertical acceleration in an elevator, you feel heavier. How much heavier? That's where the math comes in. In this particular case, accelerating at positive 2 meters per second squared, an 800 Newton person, which, by the way, that would be close to, reasonably close to a 200-pound person, would feel like they're 963.2 newtons. So we would refer to this new weight that is not equal to our real weight of 800 anymore, our apparent weight. That was one of our vocab terms a while ago that we're focusing on now. Because apparently you feel heavier. hopefully most of you could think to yourselves, yeah, I've felt this before. Because in an elevator, now an elevator is not meant to be a thrill ride. You don't experience great accelerations, and even the small ones you do experience are brief. The reason why is because the people that own the building that own the elevator you're in don't want to, the purpose of it isn't to make you sick. All right? Rapid, great accelerations easily cause motion sickness in people. And I don't think they want you thrown up in their elevators very often, so they're small accelerations that last briefly. Most of the motion you're in an elevator is constant speed, like we did in the last scenario, right? You know, if you're at rest and you're going upward to another floor above you, let's say it's a very tall building, all right, and you're going like 10 floors up. Most of your ride of those 10 floors is constant velocity. You briefly accelerate to some slow, constant speed, and it takes you steady there. Because when you're steady, you feel normal. You feel like your real weight when you're moving at constant V, up or down, okay? But it's when those brief acceleration periods occur, if it's a positive acceleration, that the scale reading or the normal force would read greater than your real weight. And of course, there's not actually a scale with you in an elevator, guys. We know that. But you could still feel this. The floor is the same thing like the scale. It just doesn't give you a reading. But we all probably could attest to the fact we've been in an elevator and kind of felt our knees feel a little heavier, like a little more pressure at times, briefly. Those are times of the positive accelerations when you're in that elevator. You feel a little heavier. We could take this to an extreme. Remember, elevators don't want you to get sick on them or feel any rushes because of this, but they do want you to feel that way on amusement park rides. When you rapidly undergo positive accelerations on rides, it might be a roller coaster or some other kind of ride where there's a quick vertical positive acceleration, you feel heavier for those brief moments. And that also causes like blood flow shifts in your body, and that's where you get feelings of rushes in your body. And those rushes are actually rushes of blood flow to or away from your brain that does give you those exciting thrill feels. But it does have to be careful. You do have to be careful because those thrill feelings, if the accelerations were too great, could actually kill you. So even on thrill rides, these are carefully calculated values on the accelerations of the ride, so you just get a thrill and don't actually physically get harmed by them. But that's the general deal of a positive acceleration, okay? Vertically speaking. Now, we have one more scenario, a negative one. So one last time, there's you, there's the scale. This time, yes, the directions never change of these things. Weight is still down, normal force will still be up. But when we are experiencing a negative type of acceleration, it turns out we will feel lighter, and we will again prove that for less. So this pushback of the scale, other words known as the normal force on you, we'll keep writing that down so we don't forget that. The normal force is the scale reading, and this is your real weight, which we're going to still keep using the 800 Newton person. And we're going to still remember from that the mass of the person is still 81.6 kilograms. We figured that out on the last page, right? So the setup equation would all look the same. The normal force minus the weight is the net total force, and according to Newton's second law, that net total force is equal to ma. Let's use a acceleration of -1. Let's say our negative acceleration is -1 meters per second squared. And just like with positive accelerations, be careful. A negative acceleration does not have to mean you're moving downward. You could be. The two ways to have a negative acceleration on an elevator, vertically speaking, is you could be going down and speeding up, or you could be moving up and slowing down. Alright, so let's do the math and plug in the numbers and prove that the scale reading would be a smaller value. The normal force would, or scale reading, would equal ma plus the weight again, but because A is negative, that makes this whole term mathematically negative when we plug in the numbers. So instead of feeling heavier and adding a number onto 800 like we did to positive acceleration rates in the last scenario, we actually subtract off because of that number being negative, and this person feels lighter. The normal force or scale reading will read only 718 newtons for a moment. And a feeling like this, even briefly on an elevator, when this happens, you might get that real brief, like, oh, my stomach is my throat feeling, like, oh, I'm dropping, right? And that causes you to not press against the scale, if there was one there, or the floor, as hard as your normal weight would in an equilibrium at rest or constant V scenario. So therefore, generally speaking, we could make what we just proved right here is that when we have a negative acceleration, the scale reading, aka normal force, will always be some value less than your actual weight, F sub G. So that's the concept. I don't expect you guys, at least at this point, to do that math for me. But I do expect that you could follow it and it makes sense for the fact of proving this concept right here. So just to recap everything as briefly as possible, we would we feel a normal weight, whatever our normal weight is on Earth, when we're at rest or constant velocity on an elevator. When you're experiencing a positive acceleration, you feel heavier, and a negative acceleration, you feel lighter. And again, these kind of rapid changes in acceleration, well, not too rapid on an elevator, is also why people get motion sickness. If you happen to be a person that gets motion sickness in a vehicle, you probably never got motion sickness in a vehicle that's moving along steady in a straight line, because you should feel pretty much the same as you're at rest in that case. People that get motion sickness in a vehicle typically happens if you're starting and stopping rapidly, especially rapidly. Doing a lot of accelerating, or even going through turns is another form of acceleration, a real windy road, turning a lot. That's because it affects the blood flow in your body, and some people are just very, very sensitive to that, and creates nausea and could even throw up. And at worst, in crazy kind of situations, super high rapid accelerations, like in car accidents, could cause internal damage to your body as well, and we may talk about that more at another time. But that's the gist of riding in an elevator that hopefully will help you for the simulation we're going to do. Now I'm going to take you through an introduction to the simulation. I'm not going to answer anything for you, but I want you to do the packet. Make sure you pay close attention to the directions. You're only supposed to do up to a certain page. I believe I listed pages 1 to 3. The final page is more mathy, and I don't expect you to do the mathy stuff on this stuff, at least at that moment. I'm concerned about the concept. So this is what we have in this elevator ride simulation. A person is, there's no scale in this one, but there kind of is because it tells you numbers off to the side. This is a person sitting in a chair in an elevator. All right, and at any given moment, it's going to show the free body diagram like we drew in our general scenarios. So you should already kind of expect what may happen in the simulation if you paid attention closely to my video and my notes. But we can click on go up to floor 10. Notice here's the floor we're currently on. Here's a status that could change, and you could even notice this little blurb coming out of the guy's head thinking what's going on to himself. Correctly answer the questions, you kind of need to look at all these together, as long as the specific numbers and what these forces are doing. When we go to floor 10, right now we're accelerating, and then accelerating downward. So if you let this thing play, this tells you what's going on. We could repeat the same ride we did if we wanted to. Notice when we're accelerating, the normal force went up, accelerating a positive acceleration. In other words, upward acceleration. And downward acceleration means negative. All right.
when it describes it there. But we could go to 420, and we have to pay attention to what's happening to these forces compared to one another. And this is what the guy's thinking. Wow, I feel heavier. Wow, I feel lighter. So it's hard to maybe look at all of these things at once. That's why you might need to repeat certain sections of the ride to accurately answer the questions. And they're general questions. You're going to put in like greater than and less than symbols, similar to like how we discussed in the notes. So please complete this by the due date. Remember, you have till Wednesday to complete this. So your assignment for Monday and Tuesday, let me say one more time, is to number one, watch this whole video, and you pretty much have if you're listening to me right now, and then complete this interactive. Do not forget that every Tuesday and Thursday at 2 o'clock, I have office hours, and will always post a link right prior to them on Google Classroom to join my office hours if you need any help. So I would advise you, if you need any help with this, please see me in my office hours on one of those days, and I will be glad to help you.